This is Computer Programming 1 from the University of Washington. I'm Martin Dickey. Welcome back. In this lecture of our course, we'll be talking about sorting. Sorting is closely related to something we've discussed already, searching. And this lecture will follow a similar format. We'll describe the problem, try to be a little bit formal about it. We'll draw a picture that describes our intention, and then try to develop an algorithm that will solve the problem using that diagram as a guide. In particular, after defining sorting today, I'll discuss some algorithms for sorting and then spend most of the time on a particular algorithm called selection sort. We'll also take some time at the end to analyze the efficiency of selection sort and make some general comments about efficiency of sorting algorithms. What is sorting? Thursdays is my laundry night. If it's Thursdays where you are, maybe you have the same problem. Before I can wash, I have to sort my laundry into piles, depending upon color and water temperature. That's what we mean by sorting in the everyday world, putting things into categories. But in computer science, we mean something a little bit different and more specific. We mean putting things in order, usually smallest to largest. We could also sort in reverse order or descending order and put things largest to smallest. When I say I'm sorting my laundry, however, I do not mean that I'm lining up all my clothes in order from smallest to largest. But that's the meaning we'll use in computer science. There are so many applications for sorting in computer science that I couldn't begin to list them all. Ordering hits in web search engines, preparing lists for output, preparing mailing, labels, and to help solve other problems. We saw algorithms for searching that required the array to be sorted, and specifically binary search. Once the array was sorted, we had a very fast algorithm. But how did the array get sorted in the first place? That's what we'll focus on today. Here's the problem with a little more formality. We have an array. Let's refer to its elements as B0 through B sub n minus 1. We want to take exactly those values and rearrange them within the array, the same array, so that B sub 0 is less than or equal to B sub 1, B sub 1 will be less than or equal to B sub 2, and so forth, all the way to the end. So B sub n minus 1 will be less than or equal to B sub n minus 2, that is, will be less than or equal to B sub n minus 1. In doing this, we want to make sure we don't introduce any values that weren't there initially, and we want to make sure we don't lose any. We'll end up with exactly the same values, the same number of values, but now they will be in order. Now for these slides, I have a notation that's not part of C syntax, but that's often useful. If I say array sub I dot dot k, that's a shorthand for all of the array elements starting with array sub I and going through array sub k. It's not C syntax, but it'll be a nice shortcut for these slides. Sorting has been intensively studied. In fact, before the first digital computers were even built, sorting was used to sort punch cards. This application goes back to at least 1890 when Herman Hollerith invented the punch cards for the 1890 census. Even in those days, entrepreneurship was rife in computing. Hollerith went on to found a startup which became known as International Business Machines. Since the early days, people have discovered many different ways of sorting data. We'll only look at one of these algorithms for our example in this course. In other courses you might take, or in other reading you might do, you may run across some other familiar sorts such as bubble sort, insertion sort, quick sort, merge sort, and there are many, many others. Some of these are just part of the folklore of computer science, have been around seemingly forever. Others, like quicksort, were invented at a particular period of time and can be dated to the time of their invention. Here's what we want. The data sorted in order, or in a picture, we want an array with this property. That's what we want. What do we start with? Well, we're not sure. We have the values in the array. We have n of them, but we have no idea what order they're in. So somehow we want to get from the bottom picture to the top picture. Along the way, with the algorithm we'll use, we'll have something sort of in the middle. That is, we'll have a part of the array that is sorted, and we're going to set up the algorithm so the sorted part is all on the left-hand or blue side. And the unsorted or unknown elements will be on the right-hand side or pink side. Now, depending upon the brand of television you're watching, this may be pink or it may be orange, but this being Seattle, why don't we just refer to it as salmon, and you'll know what I mean. The goal in constructing the algorithm is to grow the blue part and shrink the pink part. And we'll do this so that we make the blue part larger by exactly one element each time we iterate through the process. Okay? Here's what the heart of the algorithm is. At each step of the process, we can ignore the blue part because it's already sorted. So focusing on the salmon-colored part, we'll look through it, that whole salmon-colored area, and find the smallest element in it. Where does that element belong? Well, it belongs right next to and to the right of the blue element, of the blue section. By putting it there, we can expand the blue section by exactly 1 and decrease the salmon section by exactly 1. So this is the core of the selection sort algorithm. At each point, you find the smallest remaining value from the unsorted area, and you put it where it must belong. Okay. Now, if we move something just to the right of the blue area, we have a slight problem because something's already there. We can't just write over it. We have to preserve that value. And the solution we'll use is to swap whatever was there with the smallest value we've just found, which I call x. So wherever x happens to be in the salmon-colored area, I'll swap it into the kth position and swap what was in kth position up to x. By the way, my use of the word swap is not exactly accidental. If you remember, in an earlier lecture, we developed a swap function. At that time, it may have seemed a little far-fetched and not terribly useful. It seemed like just an example to illustrate parameter passing using pointers. But in fact, it's exactly what we need at this step in the algorithm. So when I get down to writing the program, I'm not going to reinvent swap, I'm just going to call it. We can identify another sub-problem, and that is finding the smallest value in the salmon-colored area. So my strategy as a programmer will be to write a function that implements this part of the algorithm. Then from my main, or it may not be called main, but my overall selection sort function, I'll have two functions I can call upon, the find smallest function and the swap function, and as we'll see, this will lead to quite a compact and simple-looking sort function. Let's focus then on the find smallest function. What it has to do is search the pink area, or salmon area, which is the values in the range k to n minus 1. Now I can assume that k is less than n. What would it mean if k is equal to n? Well, it would mean there is nothing to search. N is just past the end of the array. So if it ever happens that k equals n, I'm finished. What would I like this function to return? Well, there are a couple of ways I could set it up. But remember, we're going to follow this by a call to swap. We're going to move data from one place to another. It would be very convenient to know where the smallest value lives. That's really more important than what the actual smallest value itself is. So let's set up the function to return the index of the smallest value in the salmon area. Having done this analysis, we can now write the function. The parameters need to be the array itself, and then k, the starting position, and n, the size of the array. There will be a loop involved, and because it's a fairly simple loop, and we're counting from one position to another, a for loop might be a convenient way to structure this. Inside the loop, what I want to do is compare the position I'm currently at with the position of the smallest element that I've found so far. If the current position is smaller, then I have a new smallest element. Now, to keep track of this, let's give ourselves a variable that is always going to have the position of the smallest element. Let's call that variable pos for position. How do we initialize it? Well, this is kind of a problem because we don't know what values are there. However, I can use a trick that I've used before, and that is I can make an assumption, one that can be easily checked and changed if the assumption is wrong. So let's make the initial assumption that the smallest position is the first one. Then, as I begin the comparisons with the second value in the range, I will quickly see if that was wrong, and if so, I will change it. When I'm all done, I have very little to do. I know where the smallest position is, and I return it. Now, when we talked about searching, you remember we had a special case where the element was not found, and I had to return a special value, a -1 in that case. Do I need to do anything like that here? Are there cases where pos might not be a value in the range? And the answer will be no, if we're careful to ensure that the range always has values in it. In other words, if k is less than n. That's why I put that assumption at the top. We'll have to make sure that the part of the algorithm which calls this respects that and guarantees that we never call the function if that isn't true. Once I have the find minimum location function, minloc, the selection sort itself is really quite simple. I start out with the salmon area being the entire array, and at each step I increase it by moving k to the right one position. To do that, I need to make two calls, and you see that in the inner loop of the for loop. The first call finds the smallest value, rather the position of the smallest value, and then the second statement, the swap, moves that smallest value into position k. Once we've done that, we never have to look at position k again. We can add 1 to k and move on and look at a smaller range. A for loop is a very convenient way to write this. That's our algorithm. Let's see if it works. Let's do some tracing and see whether we get the right answer we expect. What does right answer mean here? It's not a return value that we're looking for, as we were with searching. It's a condition. It's the state that the numbers will all be in order when we're finished. Okay. Let's start with this array. If I apply the minloc function to it the first time, we'll find that the minimum value is -17. Now, k, the first time through, is 0, meaning that the range being searched is index 0 to index n-1. So, as I bring up the next part of the slide, watch carefully to see whether that swap takes place as promised. Do the -17, and the value in position 0, the 3, trade places. And they did. And doing that now gives us a small blue region. So for the next iteration of the main loop, I'm focusing my attention on the region where k starts with 1 and continues through n minus 1. Within that region, the location with the minimum value is position 2, index 2, with the minus 5. So watch carefully. Let's make sure that the minus 5 gets swapped with k, which has a 12 in it, and indeed it does. And doing that makes the blue region larger by 1. By now you should see the pattern, and you can predict how this trace is going to go, finding the next smallest value in the salmon region. That next smallest value is, before I bring it up, see if you can identify it. You should be thinking that the value is 3, and there's the location, so we'll swap that with which value? With the 12. Okay. We've just done that. The next smallest value in the salmon region is 6. Now here's an interesting case. What do we swap the 6 with? Well, don't make an exception out of it. Just swap it with the 6. There's no need to have special code for this case. The region to the right shrinks again. The new minimum value is 12. The value there is swapped with 142. Continue this process, finding that the next smallest value is 21, swapping it in place. Then we see 45. And when we finish the 45, in principle, there's still a small salmon-colored region with a single number in it, but it has to be the largest number in the array. So we can make the loop actually stop one iteration before we have processed n minus 1. And there we are. Now, did it work? To determine the answer, we should now go back to the beginning, the left-hand side of this array, and scan through it and make sure that each value is less than the value on its right. Is that true? Well, let's see. Minus 17 is less than 5, and that's less than 3, that's less than 6, that's less than 12, that's less than 21, that's less than 45, that's less than 142. So we've succeeded. We have sorted this array. We've put everything into order. Now that we see the algorithm, let's do a little analysis of it, just as we did with searching, trying to decide how many steps it took to perform the algorithm. Why do we do that, by the way? Well, it's one technique for predicting how long the function will take. Interestingly enough, we can make this prediction as soon as we get a formula. We don't actually have to code up the algorithm in order to time it. We can make a prediction purely based on this analysis. Well, let's see. How many steps are there? Every time we do a swap, we make the array, the part of the array we're searching, a little smaller. Now, its length is going to remain proportional to the original array length. It becomes shorter by only 1. This is not the dramatic reduction in the unknown region that we saw for binary search, but it is progressive. We always are making that unknown region smaller, and that guarantees us that we'll eventually finish the process and come up with an answer. Now, if you add up the total number of steps required, you'll find that it's proportional to n squared. It's actually perhaps closer to n squared over 2. Now, that's pretty expensive, even if it is n squared over 2 instead of n. Think about what it takes to sort an array of 1,000. N squared for 1,000, that's a pretty big number. And what about 10,000? Square 10,000? You might have to buy some extra zeros from eBay to write that number down. Sorting gets to be rather expensive using an algorithm like this. The issue is not whether it's correct, but whether or not we could do better. The answer is yes. We do know ways of sorting that are faster. We do also know ways of sorting that aren't appreciably faster but have different algorithms. Selection sort is about the same in this respect as insertion sort and bubble sorts that are often also taught in introductory programming courses. The more interesting sorts that really get faster we won't cover in this course, but if you go on in programming your very likely to see them. Merge sort and quick sort, for example. They take steps that are proportional to n times log n. Now, how does this compare to n squared? Well, last time I suggested you might graph n versus log n and compare those. This time you might graph n times n, or n squared, compared to n times log n. And you'll see that n log n is considerably faster. That is, as n gets larger, the number of steps required begins to be significantly less than the number of steps required in the n squared case. Well, now, what about that as a limit? Could we do better than n log n? Well, this is a case where theory and mathematics help us. It's possible to prove, in a mathematically rigorous sense, that you cannot do better than this in the general case. That is, where there are no restrictions on the way the elements may be originally ordered or the kinds of values that might be there. But there sometimes are special cases where you could do better. For example, if I have exam scores that are all in the range 0, I hope there are no zeros, but just in case, from 0 to 100, all I need would be 100 piles. I could put all the 79s in one pile and all the 82s in another pile, and then the work would be proportional to n. Okay. But most of the time, our problems don't have nice, convenient properties like that. So the general answer is that n log n is usually the best we can hope to do. It's quite interesting that we can study these questions independent of writing the programs and independent of knowing what particular language we're using. In fact, we can study these things without even knowing what kind of computer we're on, because these results hold equally well for the early dinosaurs of computing in the 50s as they do for modern microprocessors. Efficiency is one of the important issues in comparing algorithms. Efficiency means doing things in a way that saves resources. There are different ways of measuring that. Usually we are interested in the time it takes to do an algorithm or the memory it might take. Managers of engineers and programmers might also be interested in a different kind of efficiency. That is, how many people it takes, or how much time it takes a person to solve the problem. If you compare selection sort with a faster algorithm like quicksort, you see that the difference comes in the fundamental approach that the algorithm takes. There's no amount of tinkering I could do with selection sort, no matter how much of a wizard I was with C programming, that would turn that into an appreciably better sort. I might be able to shave off a little bit of execution time here and there, but I will not be able to turn that algorithm from n squared into n log n. Let's summarize what we've done today. Sorting means placing things in order and not putting socks into piles. Selection sort is one of many algorithms that have been discovered and investigated for sorting. It requires on the order of n squared steps. There are sorting algorithms which are more efficient, although they are generally more complicated to program. It's the algorithm that makes the difference, not the coding details. This is a theme that you will continue to see if you stick with computer science. I hope you'll stick with me for the rest of these lectures anyway.